Welcome back. This is video number 2 of unit number 2. In this video, we will continue our discussion on the construction of some basic PetriNet models using CPN tools. The agenda of item for this presentation remains same as of the last video in this unit. We will look at some new user-defined color sets and use them in our model. We will also look at a new feature called guard that one can use on a transition to implement some desired enablement rules for it. And we will do all of the above with the help of a very simple PetriNet model. So let us open the model and discuss these new features. So here is our simple PetriNet structure stored in a new file called mysecondpn.cpn, which is listed over here in index. It has the same structure as the one we used in video 1 of this unit. In video 1, we used the string color set, which is declared inside standard declarations. It comes standard with the CPN tools installation. In this video, we will declare some new sets and use them on this model. A new color set may be added or declared by going to the standard declaration section of index under the file name. We are already there. One may override the existing color set declarations or add a new declaration by using the marking menu command. So what we can do is we can simply override, declare or define a new color set over here, or we can right click to open the marking menu where it says new declaration, and selecting this command will add new declaration, which is empty at the moment, and we can type in the new definition of our color set. So let's construct some new color sets. I will create a new color set. The first keyword in this definition is call set, followed by the name of the color set. I'm giving it IN as the name. It's a user-defined name, followed by an equality, then another keyword with, followed by the members in this set. I'll add 2 members, capital A, followed by a vertical bar, and another member B. I can add as many members as I like by adding these bars, and then followed by the members in that set. So the definition over here, call set IN is equal to with A or B, will create a new color set with the name IN with 2 colors in it, A and B. So that's how I define the new color set. Since we are here in the declaration section, let's declare some variables also over here that we might use in our construction of this second PetriNet model in our series of CPN tools. So the declaration for a variable has this keyword var, where, and then we will have the identifiers, in1, this is the name of a variable that I'm defining. It's a user-defined identifier, and then in2 as the other variable that I'm defining. They are both separated by a comma, followed by a colon, and then the name of the set that these 2 variables will belong. So that's how I defined 2 variables, in1 and in2, to be of type color set in. Let me define one more color. This time it will be a compound color set. The one that we have just declared over here, color set in, is an enumeration type color set. The one that I'm going to declare next is called the product color set. So let me write the definition over here first. So call set, followed by the name of the color set. So let me give it a name out equals to, and then I'm using this keyword product, which will allow me to construct a product color set, and then followed by the color sets which are part of this product. So I'm using a product of in with itself, so in asterisk. Let me remove this binder from here so we can see the whole thing. In, and that's it. So what we have over here is a new color set called set out, which is of type product of, so it's a product of two color sets. Both of them happen to be IN, which we have recently defined. Now I will assign these color sets to the places in our PetriNet model. So I will assign P1 the color set IN. I'll assign the same color set to P2, and I'll assign P3 the color set out, which is the product of the color set, the previous color set IN with itself. Okay, with these color sets assigned to these places, we can now add tokens to the input places if we like. But before we do that, I would like to add some arc expressions. So let me add one B on this arc, another one B on this second arc that connects P2 to T1. This way what I'm saying is that I would need a token of value B in P1 and a token of value B in P2 for this transition T1 to be enabled. At the output, I will have an ordered pair as my token, because out is a product color set, so anything that comes to this place should have the same structure. And now I have this PetriNet structure ready to be initialized with tokens. I can now put tokens in P1 and P2. Let me put 2 tokens in P1. I'll put 1A plus 1B. This is the multi-set notation that I'm using. Please note that I have used these 2 plus signs in the middle, which is the multi-set notation of saying that I'm adding 2 tokens to this place P1. The first token has value A on it, and the second token has value B on it. In P2, I'll put 2 tokens of value B, and that's how they are put over here. Now I see T1 is enabled. If we fire this transition, let's see what happens. I'll pick the execute a transition tool. When I fire it, it fires it once, and I see a token BB appearing in P3. I see 1 token of value B from P1 gone. Similarly, 1B from P2 has also been consumed by this transition when it fired. At this point, T1 is not enabled, although we have tokens in input places. I have a token in P1 and another token B in P2, but this transition T1 is not enabled. I'm sure that you know the reason. The transition T1 requires 1B in P1, another 1B in P2, and since it does not have a B in P1 because of this arc expression over here, T1 is not enabled. It does not have the right value of tokens at its input places, at least one of them, and therefore it is not enabled and it cannot fire. I hope you understood this concept of transition enablement. We have used constant expressions on the on all the arcs. Let's use our variables that we have defined in the declaration. Over here we had declared in1 and in2 as 2 variables of type in. So let me use in1 as the arc expression on these 2 input arcs, and I'm sorry, I did not type it correctly, therefore there was an error message. I'll do the same thing with this output arc. I'll call it in1 comma in1. The reason I have this ordered pair over here is because I have out as a product color set. Let's see what happens now. Let me rewind this PetriNet and see what happens if I fire it once. When I fire it once, it has the same 1 BB token that appears in P3. I still have 1 A token left in P1 and 1 B token left in P2, and transition T1 is not enabled anymore. Let's discuss as to why do we have this situation that T1 fired only once. Let me rewind it. When we use variables on input and output arcs, what actually happens at a transition where there are variables on input and output arcs, this transition tries to bind those variables with the values of the tokens in the input places. So I have in1 over here, I have another in1 over here. Since in1 is the same variable, the transition T1 tries to assign it a value from the tokens that it finds in these two input places P1. If you like to see what values can be assigned to in1, you can click on this small green triangle, and it shows the variable binding, which is the value assigned to this variable in1 that appears on the input and output arcs by this transition. So in1, you can see that in1 can only get a value B, because if it gets a value A, or if it tries to get a value A, it can find that A in P1, but it will not get the same value from P2 because P2 only has 2 B tokens. So the only value this variable in1 can get is 1B. Therefore, these two variables are bound to this this constant or color B. And one more time, I can fire this transition T1. This is a shortcut where I did not use the tool which allows us to fire transitions. So that's how these variables are bound to token colors from the input places, and the output tokens are generated based upon those values which these variables are bound with. Since the output expression uses the same variable in1 comma in1, since in1 was bound to value B from the input, the same B will appear at the output place. So the token that appears in the output has value BB on it. Next, I will change one of these two input variables. So I'll keep in1 on this arc which connects P1 to T1, but since I have another variable also declared in2, I'll use this in2 on the second arc, and I'll accordingly change one of these two variables on the output arc. So the first one remains in1, the second one becomes in2. Now let's observe what happens when this net is executed. So let me rewind it using this rewind tool. Now T1 is enabled. Let's fire it once, and it fired with the same binding that we saw before. in1 got the value B, in2 also got the value B. Therefore we see a token at the output with those two values, in1's and in2's values, but T1 is still enabled, and this is different from the behavior we have seen before. Let's fire it one more time and see what happens. We see another token appearing at the output, which now has a value A, B. The first element is A and the second element is B, and this time we saw that this transition fired twice. Let's examine this behavior by rewinding it, and again what I'll do is I'll look at the variables and their bindings that this transition is dealing with. in2 is shown bound to B. So this transition, when it looks back, it sees that in2 variable can only be bound to one value B, and the reason is that in2 is the arc expression, or this is the variable used in the arc expression on the arc which connects P2 to T1, and since P2 has two tokens and both of them have value B on it, so there is only one possible binding, one possible value that this in2 can take, and that is B. This transition T1 shows that, but in1 has two options. in1 can take a value A, in1 can take a value B, because P1 has two tokens. One has the value A, the other has the value B. I can manually bind this in1 to value A by clicking on it. One more click, and I see that this token AB appeared at the output. So transition T1 fired with the binding that is shown on this callout box, where IN2 is shown bound to B and IN1 is shown bound to A. Okay, this transition is still enabled. I can again check the binding, and IN2 this time is now bound to B and IN1 is bound to B, because there are two tokens, one in P1 with a value B, there is another token in P2 with value B, and since there are these two variables can take those values, T1 has this available binding that it can fire with. Firing this transition with this binding produces a token at the output, place P3, which now has value BB. So the reason this transition T1 fired twice is that we have two different variables, IN1 and IN2, at the input arcs, and they can take different values. Previously we had used the same variable on the input arcs, and a single variable can only be bound to a single value. Therefore T1 could only find one feasible binding for its enablement. The next thing that I would like to discuss is the use of guard or guard expressions on transitions. Since we have only one transition, we'll see as to how a guard can be used on this transition. A guard is an optional inscription, this Petrinet, and it is used to restrict the bindings of the variables that appear on the input and output arcs. By definition, it's a Boolean expression that evaluates to true or false. Whenever it evaluates to true, the transition is enabled and can fire. Whenever it evaluates to false, that transition can never be enabled, will never fire. So if, for example, if we put a Boolean expression that always evaluates to false on this transition T1, this T1 will never fire no matter how many tokens we put in its input places. So let's use a guard on this transition T1. So let me rewind this Petrinet and add a guard to this transition. A guard is added to a transition by selecting that transition first. So I left clicked on T1, selected it, and then I hit the tab key once, and that's where I see the guard region highlighted on top of this T1 with these two square brackets. This is the guard region. I can type a guard expression over here which must evaluate to a Boolean value, true or false. So let me add a very simple guard expression over here. The guard expression I will add is as follows. I'll say N1 must be equal to N2. So whenever N1 is equal to N2, this guard will evaluate to true. Whenever N1 and N2 are not equal to 2, when I say N1 and N2, these are variables. I'm sorry, I should have used IN1 because our variables are IN1. Sorry for that. So I have IN1 and IN2. These are the variables that appear on the input arcs. I can construct a guard expression using those variables. So when these variables are bound to some value, those values are used in this guard expression, and that guard expression is evaluated with those values, resulting in a Boolean true or false. So with this guard, I can place this guard by grabbing it, placing it anywhere I like. Now if I look at the available bindings that T1 has, remember without this guard I had two available bindings and T1 fired twice. Let's see how many bindings do we have with this guard. This time it shows that there is only one feasible binding, and that binding is the one where this guard evaluates true to a true Boolean value. And if you look at it, it says that IN1 is equal to B, IN2 is equal to B, and that's when this guard expression has a true value, because we are looking for a binding for these two variables which evaluate to a true. In other words, if the two values are same, only then this expression will be true. Now we can fire it and we see that this new token has appeared at the output. So what we have done is, by putting this Boolean expression over here or guard expression over here, we have restricted some of the bindings and we call those bindings feasible bindings because those are the only bindings on which this expression evaluates to true, and T1 will fire only with those bindings, not all the available bindings. Let me just modify it a little bit, make it not equal to in1, not equal to in2. So what I'm saying is that T1 now should fire with only those bindings when the values of these two variables are different. So let me rewind it and show you what bindings are now feasible, and you can see that this time in1 gets a value A from P1 and in2 gets a value B, and that's the only feasible binding that T1 can find. If I fire it with this, I see a token AB appearing in P3, and we see that T1 is not enabled anymore because of this guard expression over here. So to conclude our discussion for this unit, we looked at some simple and compound color sets, used both constants and variables in arc expressions. We also introduced this notion of bindings when variables were used on arc expressions, and we also learned about transition guards and saw how a simple guard expression can restrict the feasible or allowable bindings for a transition firing. Here are some useful links on more in-depth information on the topics we covered in this video. See you next time in some future video.